as you know, the proposal went out 2 years ago, was accepted. We were supposed to have an in-person workshop, and we said, let's postpone it with 1 year. Nothing much happened after 1 year, so we switched. We were forced to switch to the virtual environment, and at one point we said, well, maybe we should just drop it entirely. Yet we felt that there could be interest in such a gathering. We know there are so many great seminars going on, so we then decided on a very light format, which I think Anton proposed, which was, let's have the main event to be a discussion event, which is in the afternoon, and then the talks in the morning should be just in introduction and warm up for the discussion session. The discussion session will be recorded, and we have a moderator. The moderator can prepare introductory slides, maybe setting the direction, some interesting open problems, maybe survey of whatever appear in the literature in the past year, past month, past week. And then during the discussion, we are thinking that we can address questions, cross question each other, and the moderator should keep the answers under a certain amount duration of time, maybe five minutes or so. If people wants to share slides as part of their answer, they are welcome. For sure, what we don't want in this discussion is just to have silence. So we want everybody to jump in, and the moderator to have a hard time sorting out who goes first and who goes next. And certainly we will learn as we go. Perhaps it will be a little bit chaotic today. We'll see. Maybe Johannes a formula that will work nicely, but for sure we will work, and we will learn. And by the end of the week, when we have the punchline, is there anything beyond NCG? And so that perhaps will be one of the hotly debated topic. So two talks per day, as we said, light schedule. One day we have 3 talks because one of the speaker is from Japan, so then it was too late for the local time, and we decided to start that day at 10, and that's why we have for one day we have 3 talks. So then we'll have to fight the Zoom fatigue a little bit harder that day. So let's see, Anton and Nigel, if you want to add anything, maybe I missed something.
I think so. In any case, I get to talk next. So
okay, so
if I remember, I'll say something later.
Okay, I see Jean. Let's hello, Jean. And okay, so now I took almost my 5 minutes from actually Nigel's time. So then let me introduce, pass or transit to the first talk of the day, which is it's called What NCG Can Do, and by Nigel Higson. I think it's it's a great start from for our workshop. And Nigel, you can take the link.
Okay. Everything's working. Thank you very much, Emil. You can see my beautifully crafted slides. Is that true?
Yes.
Yes. Okay, good. So, well, welcome everyone. My fellow organizers asked me to give a sort of overview of the mathematical side of this topic, which I'm happy to do. I need to emphasize that I really don't have much competence or any competence on the physics side. So this is a mathematical talk, but it's aimed at physicists to the full extent that I can manage it. And what I want to do is just focus on some topics in non-commutative geometry, specifically those that have relevance to topological questions in spectral theory. Are there gaps in the spectrum and so on? What is the index of an elliptic operator and so on? I only have 45 minutes, maybe I only have 40 minutes now, so there's not a lot I can say, and there's not a lot that anyone can absorb all at once, so that determines some limits. And in addition, half of the audience consists of experts who know just as much as me. So it's a little bit of a complicated brief. Nevertheless, I hope this lecture will be a little bit useful to a little fraction of the audience. And just a couple of warm-up remarks so that we all start on the same completely common ground. I'll be looking at Hilbert space operators, usually not one at a time, but whole algebras of operators. And of course, the spectrum of the operator is just the set of complex values for which t minus lambda is not invertible. It's a singular operator. And this talk, and to the extent that it applies to topology, non-commutative geometry, is about the topology of this set. There's more to life than topology, of course, but here we're going to be focusing on just that, on topology. And as I say, not one operator at a time, but rather whole algebras of operators will be the main theme here. And given an operator T, usually I'll be imagining that T lies inside of some algebra, some specific algebra of operators A, bounded operators on a Hilbert space. That's not absolutely necessary, but that's what mostly I'm going to consider. As for what A looks like, here are three examples. First of all, the compact operators, just the finite matrices, if you like, sitting inside of all bounded operators. So EIJ just means a single matrix unit sending the jth eigenvector, the jth basis vector to the ith basis vector. So that's the C-star algebra, which appears most often, the algebra which appears most often in this subject. Commutative algebras, like the algebra of continuous functions on a space, can be represented as bounded operators on a Hilbert space. And a lot of the intuition ultimately comes from the commutative case, although I won't really be talking about that much here. Instead, I've chosen as a running example one of the favorite algebras for non-commutative geometers, which is the irrational rotation algebra, and it's generated by two unitary operators satisfying this famous relation that means they don't commute, but they commute up to a phase, and theta should be typically an irrational number to get the most interesting algebra. So that's the sort of thing that we're going to be looking at. This particular algebra, I'm sure many of you, most of you, all of you, I don't know, exhibits all sorts of fascinating properties. There are many elements, very elementary elements in this algebra whose spectra are, for example, totally disconnected, have as many gaps as you would please. On the other hand, there are these two interesting unitary operators whose spectrum consists of the entire unit circle, and the interplay between those connected spectra of the generating unitaries and the highly disconnected spectra of typical elements, for example, typical self-adjoint elements in this algebra, is what this talk is all about. So here are two possibilities concerning, really the only two possibilities concerning the topology of the spectrum of a single operator T. You can look at the spectrum from 2 points of view. You can look at it itself, and you can ask, is it connected or disconnected? And so one possibility is the spectrum is disconnected, and that's something that's relevant to many people in many different ways. And the exemplar of that, of course, is just an idempotent operator. If you have an operator which is a projection operator onto some subspace, then its spectrum just consists of, well, at most, two numbers, 0 and 1. And well, and therefore, as long as P is not a trivial idempotent, the spectrum is 2.0 and 1, the fundamental disconnected set. On the other hand, you could look at the complement of the spectrum and you could ask, is that connected? And it's interesting to contemplate situations where the spectrum is disconnected. And the exemplar for this is an invertible element or a unitary element, not all the time. But if you have a unitary element or an invertible element which can't be deformed to the identity operator through invertible operators, then you must be in a situation like this, that the spectral value 0 must lie in a hole disconnected from the rest of the complex plane by the spectrum, just like you see in this example. Because if you could move 0 without ever touching the spectrum off to infinity, then it would be easy to construct a logarithm using functional calculus, a logarithm of the element u, and that once you have a logarithm, it's easy to contract u through invertible elements to the identity. So there are two types of topological issues we want to study. They're extremely elementary. After all, compact subset of the plane doesn't have a lot of topology. And one, as I say, is the connectivity of the spectrum, and the other is the connectivity of the complement, just like you see in these beautiful and extremely expensively produced pictures. And everything that I'm going to talk about, and everything really in non-commutative geometry, to the extent that it applies to issues in topology, has to do with an extraordinary periodicity phenomenon. Let me just, it bugs me that I didn't highlight that. Discovered by Raoul Bott a long time ago in 1959. And what Bott discovered is that the two types of topological features that I described on the previous slide are in a certain sense dual to one another. They can be exchanged in a certain interesting way. There's a periodicity phenomenon which exchanges one into the other, disconnectivity into disconnectivity of the complement, and then back again. And if you're going to go beyond non-commutative geometry, you're probably also going to have to go beyond this periodicity phenomenon discovered by Raoul Bott. And well, in order to go beyond it, it's probably a good idea to know what it really is. And so that's what I want to spend some time talking about. I just gave an example here, which is relevant to our running example. I mentioned that elements in the irrational rotation algebra very often have disconnected spectrum. In fact, you can, if the element is self-adjoint, you can label the gaps in the spectrum by elements of this interesting collection of numbers, z plus theta times z, which is dense in the real numbers. It's very interesting. And these, where do these labels come from? Well, ultimately, they come from winding numbers, and they come from winding numbers of invertible elements in a much easier algebra, namely the C-star algebra generated by one, a unitary. This is what Bott tells us. There are two different ways in which winding numbers of just functions from the circle to the circle enter into the theory of gaps, two different ways. And so one accounts for the integral part of the gap label, and the other accounts for the irrational part. Okay, so I'd like to try and describe these things to you. Here's the basic phenomenon, which is really easy, but very beautiful. Suppose you have an idempotent element, the exemplar of an element whose spectrum is disconnected. Then you can attach to it an invertible element, and the exemplar of an element whose spectrum has a disconnected complement. Well, that's not quite true. What you construct, excuse me a moment. What you construct is not a single element, but an entire loop of invertible elements, according to this simple formula, just using the exponential, which is defined using the Maclaurin series. So individual idempotents give rise to loops of invertible elements, and in a complementary way, individual invertible elements give rise to loops of idempotence according to this matrix formula that I wrote on the right-hand side of the screen. You can check rather easily that that's an idempotent. And as t varies, you get a loop of idempotence, not quite a real loop because it doesn't begin and end at the same point, but it begins at a certain fixed point and ends at a certain other fixed point, and that's almost as good. Okay, so these are the two phenomena, very elementary, that we're going to play around with. And what examined is what happens if you do one of these constructions and then the other, one after the other. Let's say you start off with an invertible element and you manufacture out of it a loop of idempotence. And then for each idempotent in that loop of idempotence, you manufacture a loop of invertible elements. So now you have a loop of loops of invertible elements, and it was all built out of a single invertible element. And in this way, you get a map from the space of all invertible elements in A, or indeed the space of all invertible elements in matrices over A, to the double loop space of the same thing, the set of all maps from two-dimensional spheres into the space of all, a group of all invertible matrices. As you saw in the recipe for one of the two transformations that I described a page or so ago, matrices are involved. If you want to build an idempotent from an invertible, a loop of idempotents from an invertible, you have to go to matrices, and that phenomenon is, we're going to see that again in just a moment. Anyway, the remarkable theorem of Bott is that these two very extremely elementary processes give rise to a homotopy equivalence, which tells you that the homotopy groups of this space, this group of invertible matrices over A, the homotopy groups are periodic in the index J, which we'll discuss in a moment. And I'd like to just spend a couple of minutes explaining how this is proved, because I believe, again, that it's worthwhile studying these basic issues, because everything else is grounded on them. And if you're going to leave non-commutative geometry for something else, you should probably master the fundamental issues in NCG before you do so. This theorem has a large number of proofs, of which I've written down several here. These little orange square boxes refer to references, which are at the end of the notes, and I'll be glad to share the notes somehow with people at the end. I'm going to discuss the so-called elementary proof, which was invented by Atiyah and Bott, but there are other substantially different proofs available, completely different, I would say, from one another, at least 4 proofs which fit into the paradigms of NCG, and which are all rather different from one another. The last one in the list here, 5, is a proof due to Joachim Kunz, which I think is somehow underappreciated, and I strongly recommend that people take a look at what Joachim did, but I'll not discuss that here. Here's the argument. I'm mainly explaining this so just to make the point that you can really keep track of details as you go through the argument. This homotopy equivalence is not some abstract thing. It's all extremely concrete. And I'm going to just discuss, as Atiyah and Bott did, this basic problem of building an idempotent back, reconstructing an idempotent from a loop of invertibles. I explained a couple of slides ago how a single idempotent through the exponential map gives rise to a loop of invertibles. And now we'd like to go backwards to really understand this periodicity phenomenon. This is the heart of what periodicity is about. So how do you do it? Well, you start off with some loop of invertible operators. And by a little approximation, this is very easy. You can reduce the loop to some kind of polynomial loop like the one that I've indicated here, the U of t. I guess I have a point of this fellow. Okay, it's polynomial not in t, but polynomial in e to the 2 pi I t. Every loop is really close to a polynomial loop just by the Weierstrass theorem, if you like, and is homotopic indeed to such a polynomial loop. So from every loop you end up at a polynomial loop, and now I'm going to focus on the degree of the polynomial n, and do what Atiyah and Bott did, which is very ingenious, namely lower the degree by 1. If the degree is bigger than 1, then of course you can do the following thing. First of all, you can write the loop as a constant matrix or constant operator A0 plus z times another loop. I'm just factoring out a z from this part of the expression for you. And now a little bit of matrix algebra tells you that the matrix U, as long as, or the operator U, as long as you inflate it into a 2x2 matrix, as you see here, can be factorized in terms which all have lower degree. And there's one other thing to say here, maybe I'll just do it here, that the left and right-handed matrices in this factorization on the right-hand side are obviously shrinkable. They're shrinkable to constant matrices just by introducing a parameter h, as I just did. When h is 1, you have the actual factorization. When h is 0, you've replaced a certain degree n loop by a degree n minus 1 loop. Degree n minus 1 loop. That's the basic idea, and you just iterate the basic idea n times, or rather n minus 1 times, and eventually every loop will be replaced by what you might call a linear loop, linear in Z loop, like you see here. This is what Tier and Bott figured out. So this is a loop of invertible operators. So for every Z, 1 minus A plus A times Z is invertible. I wrote 1 minus A plus A times Z rather than A0 plus A1 times Z, because you can easily arrange things so that the loop passes through the identity element when Z equals 1, which forces it to have this particular form. And then to say that this operator here is invertible for every Z is exactly the same thing as saying that the spectrum of A misses the critical line, so to speak, misses the line consisting of spectral values whose real part is 1/2. And so the spectrum of A has to fall into 2 bits. I suppose in principle, one of them could be empty, a bit to the left of this critical line and a bit to the right of this critical line. And now it's a simple matter to replace the A, whatever it is, by an operator which is just, so to speak, equal to 0 on this part of the spectrum and equal to 1 on the other part of the spectrum. And so you can deform A to a projection operator, an idempotent operator, and the loop U of T, you can deform to a loop where A is replaced by a P, but such a loop isn't just one of our exponential loops. That's it. That's the proof of the periodicity theorem, and it's very concrete and down to earth, and I believe there's a lot of potential for further development of this idea, because it's so easy to keep track of what's going on. So that's what Tier and Bott did. What in a separate development, actually a slightly earlier development, Tier did with Hülsebruck is to package Bott periodicity into a mathematically convenient form. He invented K-theory, they invented K-theory. The K-theory of an algebra of operators A is just it's just the collection of homotopy groups of this space of all invertible matrices. It's called GLA. There are many definitions of K-theory, but this is the easiest one to talk about. So the K-theory groups of A just tell you what are the homotopy type, or what is the homotopy type of GL of A. And according to what we just discussed, these groups are periodic. The jth K-theory group is the same as the J plus 2th second K-theory group. It only makes sense, strictly speaking, to define Kj this way when J is bigger than or equal to 1. But you can use the periodicity argument to invent a group K0, which is exactly the same thing as K2. K2 is just loops in GL of A, and loops in GL of A are all given by projections. So it's possible to invent a group K0, which only involves projections or idempotent elements, which is isomorphic to K2. All right. And what makes this theory rather compelling, and what makes it useful, and the reason that Tier and Hülsebruck did this in the first place, is that something very interesting happens if you replace or you consider not just an algebra A, but also an ideal inside of A at the same time. And if you do that, you get what we call an extension of A mod J by J. There are 3 algebras all sitting in a row. J sits inside A as an ideal, and A mod J, the quotient, is mapped to from A. And now you can recapitulate these basic constructions in the Bott periodicity theorem to get interesting maps relating the K-theory of A mod J to the K-theory of A. For example, if you have an idempotent in A mod J, you can lift it to any old element in A, find any old element of A, P tilde, which maps down to P. It may not be an idempotent anymore, but it doesn't matter. You can form e to the 2 pi I of this element P tilde, which is reminiscent of what we did in periodicity. And then you'll get an invertible matrix with entries in J, or with ones down the diagonal, but otherwise entries in J. And so the same idea that's seen in Bott periodicity, this is what Atiyah and Hesselbrook pointed out, gives rise to interesting morphisms between different K-theory groups. So the vertical morphisms in this diagram. For example, on the extreme left, you take an element, a class in K0, which is determined by a projection, and you exponentiate it, and you get a class in K1, namely some loop of invertible elements in J. And there's something similar on the other side. And those two maps are not always isomorphisms anymore, but the extent to which they're not isomorphisms is gauged exactly by the K-theory groups of the larger algebra A, like you see in this diagram. This is an exact sequence. Okay. And so this is K-theory. It's really just the Bott periodicity theorem. The K-theory is organized around one central idea, or one central difficult theorem, which is the Bott periodicity theorem, and it's packaged in this rather clever way by Atiyah and Hesselbrook. Let's take a look at how this works out in an interesting example. Let's go back to the irrational rotation algebra. So two unitary operators on a Hilbert space which satisfy this twisted commutation relation, this one here. It's a simple algebra, so it doesn't have any ideals. And so you may say, well, can't apply the Atiyah-Hesselbrook method because there are no ideals, but there's a very clever way of covering the irrational rotation algebra as a quotient of another algebra, which I'm calling here T theta. It's a sort of triplets algebra. It's generated not by a couple of unitaries, it's generated by one unitary U and an isometry V. And the isometry V and the unitary U are supposed to satisfy a version of the standard commutation relation, which is this guy here. And inside of the triplets algebra, because V is just an isometry, there is the defect projection of the isometry, the orthogonal projection onto the orthogonal complement of the range of V. And that projection P generates an ideal, and that ideal I'm calling J theta. And if you divide out by J theta, it's like you made V back into a unitary again. You made the defect projection equal to 0, and so you get A theta back. It's a very simple but powerful construction due to Pimsner and Wojciechowski. That's Pimsner and Wojciechowski there. And so you obtain one of these extensions that I was mentioning before, relating the irrational rotation algebra to a triplets type algebra and this strange ideal J. And it happens to be the case, it's actually rather elementary to see that J theta as an algebra is something extremely simple. It's just matrices over the C-star algebra in a single unitary. V disappears, so the structure of J theta is extremely easy. It's just a circle, so to speak. Not so easy is to see that T theta also has a simple structure, not as an algebra per se, but as at the level of K-theory, it just looks like also another copy of the C-star algebra generated by a single unitary. And now this exact sequence that we saw a little while ago has 66.6% of its terms elucidated. They just look like the K-theory of a circle. That's the case for the J theta terms and the T theta terms. And now you can deduce, you can infer what the rest of the terms in the 6-term exact sequence are on the basis of that. And what you find are these formulas for the K-theory of the irrational rotation algebra. So there are enough disconnected spectra to account for two independent generators in K-theory. And there are enough independent invertible elements to account for two generators in K1. Those two generators, of course, are just U and V. All right, so that's a completely typical example of how calculations are done in K-theory. One finds interesting extensions and one calculates on the basis of interesting extensions.
Sorry, Nigel, can I ask a question?
In order to make everything a little more concrete, it's useful to convert these abstract abelian groups, these homotopy groups, into elements of these homotopy groups into numbers. And this was one of Alain Kahn's great contributions to develop a general machinery for doing that. I've written down the axioms for what's called a cyclic n cocycle. Let me just write down an example to give you a sense of where this comes from. Suppose you're looking at the commutative algebra of functions on M, and suppose inside of M there is some n-dimensional submanifold. And suppose we defined phi just by integration, the integration over sigma of A0 dA1 dAn. This is an example of a cyclic n cocycle. The reason I'm giving you this example is to indicate something very mysterious and strange and wonderful about these two criteria for cyclicity and cocycleness. Whether or not sigma is closed, if you integrate over anything in the whole world that you can integrate over in the sense of differential forms, this second axiom is always satisfied. This second axiom, which looks incredibly complicated, is usually a big nothing. It's not difficult at all to handle this strange co-boundary condition. Cyclicity is what it's all about. And cyclicity here corresponds exactly to sigma being a closed submanifold, a closed cycle. And going a little bit more non-commutative, this is how these things, these cyclic cocycles arise. Suppose you have a trace on an algebra. The trace of xy is equal to the trace of yx. That's a trace. It's just a linear functional with that property. It's a cyclic zero cocycle. The fact that the trace of xy is the trace of yx is this co-boundary property. On the other hand, if you have a trace which is an invariant with respect to a derivation, if there's some one-parameter group of motions, automorphisms of A, which preserves the trace, then you can build a one cocycle according to the formula that I've written down here, using the trace and the derivation at the same time. This is a famous formula of Kant. And here's a variation which is a little more fancy. If you want to get a two cocycle, well, it would suffice, among other things, to have two derivations, two different motions which commute with one another. And then this rather elaborate formula here gives rise to a cyclic two cocycle. And each time you have one of these fellows, cyclic cocycle, I've written down a little lemma here for one cocycles and two cocycles, but it's the same for n cocycles too. Each time you have such a cyclic cocycle, you obtain an invariant, a characteristic invariant of invertible elements or of idempotence. If you take a one cocycle and you plug in u and u inverse, as I've indicated right here, then you obtain a quantity which actually only depends on the homotopy class of u. If you move u a little bit, you jiggle it a little bit, distort it along some path of invertible elements, nothing happens to this numerical quantity. And the same thing is true in the even case, if you plug in idempotence into the slots of a cyclic cocycle. So it's an engaging problem to prove this lemma. It's very educational. I strongly recommend, if you've never done it before, to prove Alain's lemma. And just to see how this applies in the case of the irrational rotation algebra, there are two obvious derivations floating around: differentiation with respect to, let's say, log u, and differentiation with respect to log v, those delta 1 and delta 2, like you see at the top of this formula. These are two derivations. They leave invariant the natural trace on in fact, the unique trace on the irrational rotation algebra, which is just given by this formula here, just the coefficient of u to the 0 times v to the 0. So we have two invariant traces which commute with one another. Two invariant, one invariant trace and two derivations which commute with one another. And so, according to what I just said before, there's a cyclic zero cocycle, which is the trace by itself. There are two cyclic one cocycles, which combine the trace with each of the deltas separately. And there's a cyclic two cocycle, which combines the trace and the two derivations according to some interesting formula that I showed you before. And they account for all of the K-theory that we saw before. There are two now characteristic numbers of K0 elements of idempotence from the zero cocycle and the two cocycle. And there are two independent characteristic numbers of invertible elements coming from these two cyclic one co-cycles. And so everything that we saw in K-theory can be turned into numbers using these four different cyclic co-cycles. It's an interesting phenomenon, which I'll return to in just a moment, that if you take the two co-cycle and you plug in an idempotent phi of PPP, like in Alain's lemma, you always get an integer. If I normalized it correctly, you always get a multiple of something. And I'll explain why that is in just a moment. In fact, almost now. Those are characteristic numbers which take K-theory and make it more concrete, which take K-theory classes and among other things, for example, test whether or not a K-theory class is zero by, if you pair K-theory class with a characteristic form with a cyclic co-cycle and you get a non-zero number, of course, the K-theory class has to be non-zero. Where do you get cyclic co-cycles from? Well, you get cyclic co-cycles from Lie theory in the way I just described, in other words, from derivations. I think it's fair enough to say that all cyclic co-cycles ultimately come from Lie theory in one way or another, if you have a liberal enough interpretation of what Lie theory is, with the exception of one other source, which is the source of index theory. And let me just say a little bit about that. Following really pioneering ideas of Atiyah, this is back in the 1960s, Atiyah thought a lot about this issue of how to convert K-theory classes into integers. And he decided that the right way to do it was to use what are now called Fredholm modules. They're not very complicated. If you fix an algebra of operators, as we've been doing, a Fredholm module is just a Fredholm operator on the same Hilbert space with one supplementary condition, which is that it should commute with elements of the algebra modulo compact operators, small operators, more or less finite rank operators. And what Atiyah observed, this is extremely elementary, it just follows from the basic theory of the Fredholm index, is that if you take the operator f and you pair it with an idempotent p in the way that I've indicated, just by compressing f by p, then you'll still get a Fredholm operator. That's what this hypothesis is all about. And so you can take its index, and that converts an idempotent p into a number, which of course is an integer. It's a Fredholm index, dimension of the kernel minus the dimension of the co-kernel of that operator. And the classes you get this way, the numbers you get this way, are not evidently related to Lie theory at all. And it's rather interesting to try and puzzle out what's going on. On the other hand, they are related to cyclic co-cycles. As Alain pointed out, you can take a Fredholm module, you can take an operator f, like I described on the previous page, and you can build a cyclic co-cycle out of it. For example, this one here, this one is indeed a cyclic co-cycle as long as f is a unitary operator. So of course, then it will have index 0, but that doesn't mean it's trivial. If f is a unitary operator, and as long as the traces here are defined, so as long as the commutators of f with elements in A lie in some small enough ideal that the traces are defined, then this formula defines a cyclic co-cycle. And the cyclic co-cycle always returns, again, if I've normalized things correctly, always returns integers when you plug in idempotents for A0, A1, and A2. Phi of PPP is an integer, and the integer you get is exactly the one I was talking about on the previous page right here. That's another lovely algebraic exercise to see that that's true, due to Alain again. And it's a fact, also discovered by Conrad at the very beginning of the story of non-commutative geometry, that the cyclic tooth co-cycle I mentioned earlier for the irrational rotation algebra, the one coming from two commuting derivations, is cohomologous to one of these index co-cycles that I've just shown you. And of course, that explains its integrality. And I think it's fair to say that in general, if you have some index problem, you want to calculate the index associated to some Fredholm operator, then to say that you are in possession of an index theorem which covers that operator F is basically the same thing as saying that the associated index cyclic cocycle is given by some Lie theoretic formula. Okay, I think that's a fair enough presentation of what index theory is all about, at least from the point of view of non-commutative geometry. How are we doing? And let me just skip this slide so as not to go terribly over time. This slide here is for my benefit. This is what I do and have been doing for, it's kind of frightening, almost 40 years. And this is the so-called Baum-Kahn theory, which has to do with understanding K-theory invariants for group C-star algebras. C-star algebras generated by the regular representation, the translation representation of a group on L2 of G. So there are two flavors of this construction. One involves just the reduced C-star algebra itself, and the other involves some twisted tensor product of the reduced C-star algebra and another C-star algebra A, and the twisting comes from an action of the group on the algebra, like I've indicated here. So one of the things we know the most about in non-commutative geometry is what the K-theory groups of C-star algebras like this look like. And there are two aspects to this. First of all, many geometric quantities related to Riemannian geometry, related to differential topology, related to representation theory. Many geometric constructions give rise to K-theory classes in one or the other of these algebras. And it's of extreme interest to know whether the classes you get are the zero class or not, or if you like. It's of extreme interest to know whether two geometric constructions give rise to the same K-theory class, or they don't. The notorious Novikov conjecture fits into that context. And the other thing you might like to know is that everything in the K-theory of C-star reduced of G comes from some geometric construction. And the Baum-Kahn conjecture, which I mentioned because it's been a defining problem in this area for 30 years or so, the Baum-Kahn conjecture addresses both of these issues. And the reason I wanted to mention it, apart from just finally writing down something that I know intimately about, is that I just wanted to make a brief comment about KK theory, which is going to be mentioned later on. This is an elaborate machine going a little bit beyond the machinery, quite a bit beyond the machinery I've shown you in these slides, and it's designed exactly to handle issues like these two bulleted issues that I've written here, and it's designed to handle or answer questions like these two questions in extremely general situations, for example, for Lie groups of very high rank or manifolds of very high dimension, fundamental groups of manifolds of very high dimension, that kind of thing. And it's a big machine and it's very powerful, but it's not clear to me that it's the right machine for more down-to-earth problems related to lower dimensional geometry. Anyway, let me not say any more about this particular business. I want to close with well, I guess I am going to say a little bit more about that. I want to close by giving an example of a calculation in K-theory, which was done by Alain in 1981. This calculation was rapidly subsumed by Kasparov's theory. This calculation was first done by Kahn and then redone by others within the framework of KK. But I think it's worth examining how calculations in low dimensional cases like this is a calculation involving the group R, the Lie group R, how calculations can be done very concretely by alternative methods, not using the big machines, but using much more explicit formulas. And so I'd like to suggest this as an instance of a calculation that also bears some further study. So what Kahn did, as you see at the top of the slide, is he calculated these twisted tensor product C-star algebras, cross product C-star algebras, which arise the K-theories of these C-star algebras, which arise whenever you have a one-parameter group of automorphisms on an algebra A. If you have a one-parameter group of automorphisms on A, then you can form something called C-star of R comma A, which I mentioned before, this twisted tensor product. And it turns out the K-theory groups of the twisted tensor product are the same as the K-theory groups of A alone, with a dimension shift. So projections correspond to unitaries or invertible elements correspond to projections under this isomorphism. And there are two ingredients in the proof, and I'm not going to say much about the first one. I just want to point out, say, one more slide or two more slides about the second one. This is a wonderful observation of Alain. Suppose you have a projection or an idempotent E. I think it's called P on the next page, but it's E here. And it therefore defines an element in K0 of A. So it's something on this side of our isomorphism. And you'd like to build a corresponding element on the other side of the isomorphism. So you'd like to build some invertible element in the C-star algebra cross product, as we called it, the twisted tensor product, to which that projection should correspond. And so how are you going to do that? Well, Kant argued that if you're in the situation where this projection was actually fixed by the one parameter group of automorphisms, then it's rather easy to see how to construct a corresponding invertible element. Not only is it easy to see, but in fact, there's only one possible choice. Assuming the isomorphism here is functorial, there's one and only one choice that can be made if you're in this special situation where the projection is fixed by the R action. But of course, typically a projection isn't fixed by the R action. And this lovely lemma of Kant tells you that you can do the following thing. You can change the R action to get rid of that inconvenient fact. Namely, you can replace the R action by an extremely close by R action, a so-called exterior equivalent action, which does fix C. And then you know what to do to build a K-theory class over here. And the reason that's significant is that well, first of all, here's a page explaining what two exterior equivalent actions are. It just means that the two actions, it's maybe best to study the formula at the bottom here. It just means the two actions are related by some inner automorphisms, by one cocycle, so to speak, of inner automorphisms, exactly like you see in this formula. You can express it pithily and elegantly using 2x2 matrices, which is, this is something from Alain's von Neumann algebra days. These two ideas are related to one another. If you have two exterior equivalent actions, then they give rise to equivalent, in fact, isomorphic cross-product algebras. So you don't actually cause any damage by changing an action into an exterior equivalent action. You don't change the K-theory at all. And therefore, if the lemma is to be believed, this lemma of Alain, you can always assume, given any projection, any idempotent, that the action fixes it. And then you know what to do, and you can define the map, and you can prove Alain's formula for what the K-theory of the cross-product algebra is. And I just want to write down this lovely formula. This is a perturbation expansion for what the cocycle should be, which again has the merit of being extremely explicit as compared to the methods of KK theory. So if you have a projection E, and if delta is the generator, the derivation, which is the generator of the one parameter group of automorphisms with which you start, then you can perturb the one parameter group of automorphisms by this unitary cocycle according to the formula that's written at the bottom here. And now the new alpha prime of t actually fixes E if U of t is defined in this elaborate way here. And then you know how to build Kahn's isomorphism. So there are here and there, if you look back into the 1980s, beautiful methods in non-commutative geometry and K-theory, which kind of got forgotten when K came along and people like me started to think about Baum-Kahn conjecture and so on. And we used all these highfalutin methods, but these older and more concrete methods, I think, bear some re-examination. Okay, and so just in conclusion, at the end of this brief introduction, let me say that topology intersected with non-commutative geometry equals basically the Bott periodicity theorem. Let me say that we can, thanks to Alain's work in cyclic theory, make specific and explicit numerical formulas out of K-theory formulas, and in index theorems too out of K-theory formulas, again using cyclic co-cycles. And finally, that although we have an elaborate theory, KK theory, which handles extremely complex examples and has made extraordinary progress, for example, in the Novikov conjecture, it's also worth remembering that in simpler contexts, simpler here means related to groups which are not simple groups, but more elementary groups, for example, the group of real numbers. There are some older methods which are relatively unexplored and one may profit by thinking about them further. All right, thank you very much.
Let's thank Nigel.
Any questions from anyone? Since I'm also an organizer, I guess I can ask them.
Yeah, right. Okay, Renato, you can unmute yourself and ask the question.
Renato.
Hello, Nigel. Thanks for the talk. It was very illuminating. I'm just wondering, I'm a mathematician, a topologist, so I'm more used to topological K-theory. And I was wondering, in topological K-theory, you have a natural product induced by the tensor product. I don't know
if I'm supposed to be hearing anything, but I can't.
Oh, you cannot hear?
In fact, maybe that's my fault. Let me just try some.
Are other people hearing me?
Yeah, I can hear you for sure.
Zoom maintenance here. Okay, hang on. Let me. Okay, I'm sorry. Please repeat the question. I can't hear anything.
Can you hear me now?
I can. It was my fault.
Okay. I'm a topologist, so I'm more used to topological K-theory.
Yeah.
In topological K-theory, you have a natural product induced by the tensor product of fiber bundles.
Yeah.
I was just wondering if you're aware if there is an extension of this multiplicative structure to non-commutative C-star algebras.
This has been extended to the fullest extent possible, but so yes, there are products. They don't exist to the same extent that they do in ordinary algebraic topology. There is no diagonal map, and if you have a space X, you can embed it in X times X along the diagonal, and that's really where products come from. There's nothing quite like that in general for non-commutative algebras. And so it's not the case that the K-theory of A is a ring. However, there are various multiplicative structures which do persist, and Kasparov organized them all into this grand KK theory.
Mm. So is it the case that it's not known how to do it, or is it there?
Oh, it's known
that it doesn't exist.
They don't exist.
Okay.
K-theory for non-commutative algebras has an extremely simple structure. For example, just to tell you something which may disappoint you as a topologist, there are no operations in K-theory of C-star algebras. In K-theory of operator algebras, there are no natural transformations from K-theory to itself, except for multiplication by 3. So that shows you that although you're allowed to apply K-theory to many, many more objects, various non-commutative spaces, the price you pay, if it is a price, is that the groups you get are much lesser things. They don't come equipped with rich, structures, rich families of operations.
Okay, thank you.
You're welcome.
Any questions? I will. There one question. I like your introduction where you link the Bott periodicity with spectral problems, and you mentioned that one several times to me. It was not very clear, but now I think I got a clear connection between both periodicity and spectral problems.
Mhm.
And here is one problem which I am facing many times when working with models. If you have an operator and the spectrum is the full real line, can we say anything about this spectrum? Now you can close it going up or close it on the bottom, and you have the
Well, if you take the Cayley transform, for example, of such an element, now you have a unitary whose spectrum is the entire circle. And so that Cayley transform has a chance to represent a non-trivial element in the K theory of some algebra. That's exactly what happens, for example, for I times d by dx on the line. There is a relevant K-theory group into which that Cayley transform lives, and into which that Cayley transform goes, and it in that relevant K-theory group, it is a generator. And so the fact that it is a generator proves that there is no gap in the spectrum of IDDX. I mean, that's of course a toy model example, but it indicates that, yeah, that you're immediately in the position to apply K-theory then.
How about suppose you have an operator which has more than one self-adjoint extensions. Those characterize in the formalism you presented? More
possible. I mean,
indices and so on.
So one possibility is to attach to a single operator a family of self-adjoint extensions, and now let's say parameterized by some space X. And then you take the Cayley transform of each of them, like I was just saying. Now you have a family of unitary elements parameterized by some space X. And that family gives some element in the K-theory of X, tensor, C of X, tensor, whatever the C-star algebra is. So for example, the theory of spectral flow, maybe that's not a good way of putting it. This can be related to the theory of spectral flow. If you take the operator of IDDX not on the line, but just on an open interval, then there's a circle's worth of self-adjoint extensions. And that circle's worth of self-adjoint extensions gives a circle's worth of Cayley transforms, and that is the generator of some other K-theory group. And the non-triviality of that K-theory element can be measured, for example, by spectral flow or by one of these cyclic co-cycles I was mentioning.
Thank you. Okay, let me check the chat. I see two. Okay, Ralph has a comment. Trout's picture of K-theory may be relevant to Emil's question. What?
Sure, Jody's. I should know what you're referring to, Ralph, because Jody was my student. But what picture? I'm not quite sure what the picture of K-theory is that you're referring to.
I have worked out and also with you about these odd self-adjoint operators, maps from this algebra of C0 functions on R into another target C-star algebra.
Ah, okay. So that's what yeah, okay. So I'd call that the spectral picture of K-theory, that kind of thing.
Okay, and Ulrich put up a reference, or maybe a reference with a question, and Ralph has to confirm, is this one here?
Yeah, okay, then this I know it. Yeah, I think that I agree with Ralph that this, I'm looking at the paper that Ulrich posted in the chat. This is certainly relevant to what I just said.
So let's see, we have the next talk at 12, but since we have Nigel here focused, maybe we can try a few more questions. Definitely, if you, for example, for me, the very last slide where you put this co-cycle related to quantum, to what extent that characterizes the automorphisms we start with. In other words, if we apply it on the whole classes of KK theoretic, is that the image through that characterizes the automorphism completely or not?
And I'm trying to, so I don't understand the question yet. We're imagining we're starting with a one parameter group of automorphisms of A, is that right?
That's right.
And now each time we have in our hands a projection operator, we can build a one cocycle according to Alain's formula. And you'd like to understand that process, which takes an idempotent and builds a new dynamics?
So now let's say, in your language, I will say you get characteristic numbers, and you apply on all available idempotents, you get all possible characteristic numbers.
Okay. Mm-hmm.
Is that completely characterizing the automorphism or not, that you started with, or up to what?
I would say that it would be difficult to see which automorphism you're dealing with just by looking at characteristic numbers, because if you continuously change the dynamics, you continuously change this one parameter group of automorphisms. For example, you shrink it down to a trivial one parameter group of automorphisms. As you make that continuous change, maybe it's not completely obvious from what I said, but these characteristic numbers aren't going to change at all. In other words, the characteristic numbers won't see the automorphisms one bit.
Oh, okay.
It's sort of, sadly, it's exactly the opposite of what you might be hoping for. These cyclic cocycles to build the cyclic cocycle, to actually write down a formula for it will certainly depend on what the dynamics is or are, but the numbers you're going to get at the end are not going to be terribly informative about what the dynamics was. So you have to do something different. You have to look at the formula, what the cocycle is, not what it gives, how it's defined, not what values it gives on say on idempotents.
Do we have time for a question?
Yes, Johan.
Also in this context of the quantum isomorphism, if I recall, you say it's all very explicit, but if I recall, in order to apply something to a projection, so into K0 of the algebra, in order to get something in of K1 of the cross product,
yes,
the more or less explicit formula gives me something in K0 of the suspension, right? So my question is, can I really stay downstairs? Or do I have to see that in the suspension?
So yeah, that wouldn't bother me a bit, the suspension. I would say that the effect of this cocycle trick that I tried to show is to reduce the more complicated problem of understanding a cross-product algebra to Bott periodicity. But then you have to deal with Bott periodicity, and so it's not going to be any more explicit than these periodicity maps are that I was describing at the beginning of my talk. So what Kahn does is make the understanding of a cross-product algebra no more complicated than understanding Bott periodicity, but he doesn't, as for Bott periodicity, he doesn't improve on that. And so I think the problem you're referring to will persist. Yeah, if you don't like having to deal with some suspension, some loop of invertibles, let's say, instead of a projection, if that troubles you, then yeah, you're going to continue to be troubled.
Yeah, it troubles, because if you want to apply it to physical situations, there's a big difference whether I talk about a projection or about a unitary loop. I mean,
yeah, I mean, I'm not maybe in a position to comment on that. I mean, I did try to say that the process by which you convert a unitary loop into a projection is kind of mechanical. I mean, there are many stages involved in this proof that Thier and Bott gave that it can always be done. You can always reduce a loop of unitaries to a projection. It's sort of mechanical, but it's elementary but not simple. How about that? It's
That's okay.
Good. Okay, so we took 5 minutes from Peter talk, but